So let's deal with a slightly more complex problem than the first one that we looked at. So here we're looking at a simply supported beam because we have a pin and a roller, but now our applied load is a bit more complex. Here we have a uniformly distributed load with the intensity of W acting over the entire length of the beam. So instead of having a point load, we now have a distributed load, which adds a little bit of complexity, but at the same time, based off the ideas that we talked about in the last problem, we should already know a couple things about the nature of the shear diagram and the moment diagram. Remember, with the single point loading that we looked at previously, there was no distributed load, and therefore the internal shear was a constant function. The internal moment was a linear function. Here, because I have a constant distributed load, that means that my shear should be linear and that my moment should be parabolic, because this is a function in terms of x to the 0 power, it's constant. This is like x to the first power, and therefore this should be x to the second power, parabolic. Now, we'll do the math. We can't just rely on that for the final answer, but I mean, we should expect to start seeing some curved lines once we get to the moment. That same thing is going to apply later on. If we had a linear externally applied distributed load, then we'd have a parabolic shear and we'd have a cubic moment equation. So good things to think about before you start working through the problem, making sure that the order of your x variables agrees with what you expect. All right, so here, just like with the previous problem, we're told that we should be measuring x from the left side of the beam going positive to the right. So just to be really clear, if this is point A and if this is point B, then A is where x equals 0 and B is where x equals L. Now, in order to figure out the internal shear and internal moment, I need to make a section cut at x, at a variable distance x. Now, that means I can choose to either keep everything to the right or everything to the left of that section cut. Now, here I have to have at least one support reaction either way, and if I keep everything to the right, it doesn't really add a lot of extra value because now I have to deal with slightly more complex geometry, and it's probably not worth it, but you would get the same exact answer either way. So for me, it really makes the most sense to do a free body diagram keeping everything to the left, and that's going to look like this. Section cut right there. Assumed direction for internal shear. Assumed direction for internal moment. And I need a little bit of other information here. I need the length here. Well, that's just x from point A to the section cut. That distance is x. I need things like my coordinate system. No reason to deviate from our given. And I need to have my support reaction. There's no way to get around it. I can't choose everything to the right of the section cut and avoid it because there's a roller over there as well. Now, the horizontal support reaction we know is going to be 0. There's no horizontally applied loads. The vertical reaction we'll talk about in a second for either of these. So AY and BY, the way that I would solve for those, and I'll need AY over here, the way that I would solve for AY and BY is using the global free body diagram. I can't figure it out here. There would be too many unknowns. I need to solve for AY and BY using the global free body diagram. This is where a lot of students run into a conceptual issue because to solve for that, I need to turn this distributed load into a resultant load. And that's going to be acting right at the middle of the beam. That resultant is going to be equal to W times L. That resultant force, W times L, acting at the midspan of the beam, will allow me to then say sum the moments about B to solve for AY. And that's relatively easy to do. AY is going to be equal to WL over 2, and BY is also going to be equal to WL over 2. All right, so far, relatively straightforward. The issue is going to become, well, I just made a section cut right here. I'm making my free body diagram. I have my reaction on here. When it comes to showing the applied loads, a lot of students will look at this and say, we're done. Because I turned this distributed load into a single point load, and here my section cut hasn't made it all the way over here yet, and therefore I don't need to show any load here. That's erroneous. That's incorrect, because this section cut passed through this distributed load. This point load is only equivalent to this distributed load if for the reactions. When it comes down to the moment diagram, the moment equation, and things like that, you can't rely on this point load anymore, because you're only looking at, in this case, we're only looking at everything to the left of the section cut, which is only this piece of the distributed load. So I can't use this resultant specifically for this free body diagram because it represents load, some of which is not there. So what I'm going to do is I'm going to draw like a dashed line to show the remainder of that distributed load that remains. It still has an intensity, a height of W, that doesn't change, but this is all that remains. I need to turn this, the remaining amount of load, into a resultant. And the way that we calculate the resultant is the area of the distributed load. Well, the height is W. The length of it is not L anymore. The length of it is just X, because all the rest of that load over there, it's gone. I don't get to take it into consideration. So the resultant equals the area, which is W times X. The other important factor when we look at resultants would be, where is that acting? Well, this is rectangular, so the centroid is at half the width, and so I can write down I have X over 2 to the right, and I have X over 2 to the left. That is where that resultant load is acting. So don't forget about a distributed load that you turn into a resultant. You always have to look back and say, is my section cut passing through that distributed load? If so, you need to restart over calculating your resultant here. And the point of the section cut I often call point O, so I'll label that as well. Okay, so now we're done with the free body diagram. Now we've got coordinate system, internal resultants, externally applied loads, support reactions, geometry. We're good to go. So in order to solve for V and M, I now need to run equilibrium using that free body diagram information. So to solve for V, very straightforward. Sum the forces in the y direction equal to 0. Based off my coordinate system, up is positive. So here I have AY going up, so plus AY. AY has a value of WL over 2. Downwards, I have this resultant force. The resultant force has a magnitude of W times X, so minus W times X, and then minus V. With a little bit of algebraic manipulation here, I get that V equals positive WL over 2 minus W times X. That is the function for the internal shear. Now here, if I want to find the internal moment M, the best place to sum the moments about, not the only place, but I think the most efficient place, is the section cut itself that I often call point O. So if we sum the moments about the section cut equal to 0, well, AY here certainly causes a moment about O. It's a clockwise moment about O, so it's minus. The force component is WL over 2, and the distance component is X. Here, the resultant due to the applied load going downwards is causing a counterclockwise moment about O, and so that'll be plus. The force component is W times X, and the moment arm is X over 2. V doesn't cause a moment about O, but M sure does. It's a counterclockwise internal moment, so plus M. So with a little bit of rearranging here, I get that M equals negative WX squared over 2. That's this term right here. It becomes a negative when it goes to the other side, plus WLX over 2. And that is the internal moment equation. Just based off one free body diagram and then 2 equilibrium equations to figure it out. Okay, so I've got my equations. You could plug in, this is all variables, but you could plug in values to make sure that everything is in the correct units, but this should be in units of force. This should be in units of force times distance if you want to double check your work. All right, so now we can get to the plotting part of it. So just like before, I can use my equations to plot everything out, and then we're going to check our work by the rules that we've talked about before. Change in internal shear equals the applied point load. Positive would be a point load going up. Change in moment at a discrete location would be equal to a couple moment, and that would be clockwise. Couple moment would cause a jump up in moment. We also say that the slope of the shear diagram equals the intensity of the distributed load. And then finally, the slope of the moment diagram equals the intensity of the shear at the same location. I'm just going to plug in a couple of values. This is a linear equation. Look, this is w times x to the first power. This is parabolic because the highest order x is x squared. And so this is linear, this is parabolic, exactly what we anticipated based off our rules relating externally applied loading, internal shear, internal moment. And so what I get if I plug in x equals 0 here is I get a positive WL over 2. If I plug in x equal to L, I get negative WL over 2, which would be this point right here, minus WL over 2. Now, because that's a linear equation, if I have 2 points, I can simply just draw a line connecting them. Okay, so there's my shear diagram. We'll check it with these rules in just a second. With the moment diagram, here I could plug in a few different values. I could plug in x equals 0. That would be 0 plus 0, so it'll start out at 0. If I plug in x equals L, I will also get a value of 0. But don't let that make you think that this is going to be a constant 0 value the whole way. That only applies if this is a linear function. It's parabolic. And so because I know that the slope of the moment diagram equals the shear, that means that the moment should be at a local maximum or minima where the shear equals 0. Where the slope equals 0 is where you get a local maxima or minima. And because shear is the slope of the moment diagram, here where the shear equals 0, which I can easily calculate is at L over 2, this location has to be a local maxima or minima for the moment because shear is a slope of the moment diagram. So with that knowledge, the location of the local maxima or minima, I plug in L over 2 to my moment equation and I get WL squared over 8. You're probably going to get used to that value because a uniformly distributed load on a simply supported beam will always give you a maximum positive moment of WL squared over 8. And because it's parabolic, I should get a shape roughly like this. Now a question that I'm going to get would be, well, how do you know it's parabolic like this and not parabolic like that? Well, first off, I calculated 3 points. The only way it could fit is concave down like this. But the other bit of information that we should talk about to kind of check our work here would be, does our 2 diagrams agree with all of our rules here? So let's kind of go through the process. So if I start at 0 and end at 0, as I go from left to right across my beam, if I start at 0, the first thing that I see, and actually, so this is where I need to complete my loading diagram. I forgot to include the vertical support reaction WL over 2 and the vertical support reaction WL over 2 at point B and at point A. So start at 0. First thing that I see from my shear diagram is my support reaction at A going up with a magnitude of WL over 2. So I go from 0, I go up WL over 2. That confirms the value that I got from my equation. Well, between A and B, there's no point loads applied, but there is a uniformly distributed load applied. So from this equation, I can also say that the change in shear between 2 points equals the integral underneath the loading diagram between the same 2 points. So this is just saying the area underneath the distributed load. That's this entire area of this rectangle. But keep in mind those arrows are pointed down, so it's a negative area. So this area that we're talking about right here, the area equals the integral, which equals minus W times L. Because the height is minus W, the length is L, and so that means that the change in shear from here to here is minus W times L, which is, if I minus W times L from positive WL over 2, I confirm this value right here. And it has to be linear because this is constant distributed load, so this has to be a linear shear diagram. And then at the very end, I have WL over 2 going up, start at negative WL over 2, jump up, that's how I get here. That's a negative value, just to be really clear. All right, what about the internal moment diagram? Well, nowhere do I have a couple moment on this beam. We did for the cantilever, but for the simply supported beam, there's no moment reaction. There's no applied couple moment. So this is true, but we don't have any, so it's not really important. This equation is going to be really important. So this is the change in moment equals the integral under the shear diagram between the same 2 points. Well, starting out at 0, there's no couple moment. This doesn't jump up or down. But I do know that the slope of the moment diagram equals the shear. So I know that the slope right here has to be positive because at this location, the shear has a positive value. So it starts out with some positive slope. Eventually, that slope will decrease because the shear is decreasing. So that's why this is getting shallower and shallower. And right here at L over 2, it's going to be 0, which means that it maxes out. And the slope continues to get larger, but in a negative sense. And that's why the slope is doing this. Now, if I want to know the change in moment from this point, which we know is 0, to this point, which we know would be a local max or minimum at L over 2, all that I need to calculate is the area underneath the shear diagram between those same 2 points. This is A, this is B. I'm just going to call this intermediate point C. So the change in moment from A to C is the area underneath the shear diagram between the same 2 points. This area, it's positive because it's above the horizontal axis. It's a triangle, and so it's 1/2 the base, which is x over 2, times the height, which is WL over 2. Multiply this, I get WL, this should be L over 2, not x over 2. L over 2, I get WL squared in the numerator, I get 8 in the denominator. So I go from 0, I change positive WL squared over 8, which is why my overall value is positive WL squared over 8. And you can see due to symmetry that this is going to be the same magnitude, but on the negative side, so I go from positive WL squared over 8 minus WL squared over 8, the area of this triangle, and I end up right back here at 0, which is what our kind of procedure tells us has to happen for both shear and moment. Start at 0, end at 0, and then follow all of these rules in between.